In this topic, we are going to cover undocumented API calls. Not all Windows APIs are consistently documented on MSDN. The well-documented APIs that we have used so far operate in user mode. However, when calling a Win32 user mode API, we will usually eventually end up in kernel mode. And that's because the Windows APIs are just an abstraction layer over the native API. And the native API is the lowest level available to us in user mode. And it's just a bridge between user mode and the underlying Windows operating system. Before this separation between user and kernel mode existed, a small application crash could cause your entire Windows system to crash. And while not always clearly documented, researchers have made prototype definitions publicly available on the internet. However, Microsoft could decide to change these at any time if they wanted to. And these native API calls that we are interested in are defined in NT-DLL. And one of the benefits for a hacker of using the native API is that the native API can be used to evade endpoint detection and response tooling, which could be, for example, hooking user mode function calls. So let's switch back over to the virtual machine and see how this works in Python. So far, when interfacing with the Win32 API, we have been relying on and using the official Microsoft documentation. We use the documentation to understand how the functions work, the expected inputs, outputs, and error messages. However, not all of these Windows functions are officially documented. And so to demonstrate the difference between using the official MSDN documentation for user mode calls and the unofficial, sometimes undocumented API for some of those function calls, we are going to use virtual alloc and the virtual alloc function reserves, commits, or changes the state of a region of pages in the virtual address space of the calling process. So basically, what that means is that we can use virtual alloc to allocate memory. So let's start by importing from C types and Win types. And rather than specifying the exact Win types this time, let's just import all of them. We can save this. And let's also set up kernel 32, as we will be using this quite a bit in this lesson. And let's also define a variable, size_t. And this is just cosmetic, but will make it easier for us when using Windows types and C types interchangeably. So let's first define virtual alloc as per this MSDN definition. Next, we need the archetypes. And we take in an LP void, a size t, a d word, and a d word. And we can also see the expected return type. If the function succeeds, the return value is the base address of the allocated region of pages. So we can use an LP void here, which is just a pointer to a void object. And now we need to know what parameters we need to pass to this function. So we can see we need an LP address, which is the starting address of the region to allocate. And if this parameter is null, the system determines where to allocate the region. So we can just pass in null here because we don't care where this memory is allocated. The next parameter, DW size, is the size of the region in bytes. Next, we need the allocation type, which specifies the type of memory allocation. So let's copy over these constants here, mem commit and mem reserve. And lastly, we have FL protect, which is the memory protection for the region of pages to be allocated. So we can take a look at these constants here. And let's use page execute read write. Which enables execute read only or read write access to the committed region of pages. And now that we have our constants defined and the virtual alloc function defined, we can call it. So we can create a new pointer. We pass in none as our first variable, the size of the region, the allocation type, and the protection type. And we can check for errors. And if there's an error, we can print that out. So this is helpful for debugging. We can also print out where we have allocated our memory. And we can specify an input here so the Python process doesn't die. And now we can execute this. Fix a typo here. And here we can see that we've allocated memory at this address within our Python process. And in order to verify this, we can make use of Process Hacker. And Process Hacker is a free, powerful, multi-purpose tool that helps you monitor system resources, debug software, and detect malware. Basically, Process Hacker is a more robust version of the Task Manager. So we can download this. And if you haven't already installed it, you can follow the installation instructions and launch the application. And now we can filter for the Python process. And we can see information about the process's memory. So we can go to this address. And here we can see that we have 4 kilobytes of read, write, execute memory, which we have assigned within this process by using the virtual alloc function. And so in general, this is how we have been operating with the Win32 API so far. We find a function we want to use on MSDN, create the function definition in Python, and use the function. And this works fine, but depending on our use case, this might not be a good approach. For example, a number of antivirus and endpoint detection and response solutions make use of API hooking to gain telemetry for their analysis when trying to identify whether an application's behavior is potentially malicious. So how can we get around this? Well, it depends on the function and your use case, but one approach is to use a lower level API call, which may not be being hooked by the security product. The API calls we have been using so far are coming from userland in kernel 32. And then behind the scenes, they are being translated into a lower level API call in NT-DLL. As a user, we don't really see this happening, but behind the scenes, the operating system is doing a lot of work for us. And as already mentioned, these APIs in NT-DLL are mostly undocumented. and can change at any time with a new Windows release. So be careful if you are bypassing the official Win32 API in user mode. So with that in mind, let's translate that same virtual alloc call down a layer deeper and directly call the NT-DLL version of the virtual alloc function NT-allocate virtual memory. And NT-allocate virtual memory is a good place to start because this function is documented on MSDN. And so let's start trying to interface with this. Let's have a reference to NT-DLL. We can also define an NT status, which is a D word. And now we can start working on the function definition. And here we can see the expected argtypes. And the return type. And here we can see the return value returns either status success or an error code. And these are the potential error codes that we could see from calling this function. And now that we know how the function is defined, we need to understand how we can interface with it. So the first parameter expected is a handle for the process for which the mapping should be done. And to get a handle to the current process, we could make use of the getCurrentProcess function. And this function retrieves a pseudo handle for the current process. And this is defined as a special constant. And that constant is 0x and then 16fs. So this is the pseudo handle we can use. And now we don't need to call this function. The next parameter that we need is a base address, which is a pointer to a variable that will receive the base address of the allocated region of pages. And if the initial value of base address is null, the operating system will determine where to allocate the region. So we can create our base address. Next, we need the number of high order address bits that must be 0 in the base address of the section view. And we can just enter 0 here. Next, we need our region size, which is a pointer to a variable that will receive the actual size in bytes of the allocated region of pages. And let's create a larger section here so we can see it more clearly in Process Hacker. Next, we need the allocation type, which is the same bit mask and constants which we used before for virtual alloc. And similarly, for the protection, we can also still use page execute read write. So now we know how to call this function. So let's do that. We can pass in our pseudo handle, the reference to our base address, a 0 bits, reference to our size, our allocation type, and our protection. We can again verify that this succeeded. And if we don't have any errors, we can print out our memory location. We can run this. It's typo. Picks up checking pointer 2 here for the NT status, not pointer 1. And so here we can see that we've now allocated memory using virtual alloc and by directly using NT allocate virtual memory. And we can verify this in Process Hacker by looking at these memory addresses. And here we can see the 4 kilobytes that we allocated with virtual alloc, as well as the 12 kilobytes we allocated with NT allocate virtual memory. And we can also verify our error handling. So if we changed our sudo handle value, we can see that we now get an error message here with an error code. And this error code translates to an invalid handle was specified, which makes sense. And depending on your use case and what you are trying to achieve, leveraging the undocumented API can be useful. So for example, if you're trying to avoid suspicious API calls or trying to avoid some security product. However, when using undocumented or less documented APIs, always remember that the function definitions can change without notice. So if reliability and future-proofing is more important, you should rely on the standard Win32 user mode API. However, like most things in security and programming, if you don't want to, you don't really have to, as we've just seen. But that's it for now, and in the next lesson, we are going to cover direct syscalls.